I'm Nick Evans. I'm a data scientist at Shopify. I'm here to tell you about real-time risk management using Kafka, Python, and Spark streaming. A little bit about myself. Shopify is based in Ottawa, and I'm from Northern Ontario, which is Canada. I like the cold. I like hockey too, in case you couldn't tell by the backgrounds that showed up when I first plugged in my computer. And the hat too. I was actually going to wear my jersey, but I decided against it because he might not take me seriously. It's in my case over there though. So Shopify is a commerce platform. So if you make a hat like this nice hat here, and you want to sell it online, you go to shopify.com, sign up for a store, take a picture of the hat, and then within probably I'd say 2 minutes, you can start accepting credit card transactions. We do a lot of other stuff like shipping, integrations with Facebook, other things like that. And if you become really successful and you have enough money to buy a brick and mortar store, you can actually install our app on your iPad, get a cash register and a credit card swiper, and just accept credit card transactions from your physical store. So on that note, underwriting credit card transactions is actually pretty risky. There's a potential for loss if a stolen credit card is used to make a purchase, as the bank recovers the money from us. That's called a chargeback. If a merchant doesn't have enough money in their bank account, then we end up having to foot the bill. It's also possible they might sign up and then accept fraudulent transactions and then leave. And then how do we get the money back? We can't. So they also might create a fake product that they never intend to ship and then sell that to unsuspecting customers. And then we end up footing the bill there because they usually disappear before the chargebacks come in. They might say oh, this product will ship in December 2016 and then be gone by January. January 2016. Where's my mouse? There it is. So we need to be quick at this underwriting. We pay our merchants the money that they capture through credit cards, I think about 2 or 3 days after they capture the transaction. And we need to check these credit card transactions and stop the bad actors from stealing money from us. The problem is that the vast majority of these transactions are actually legitimate because there's a lot of good people in the world. And we also have a ton of transactions. And we really don't want to punish the good merchants by holding back their money longer than we need to. They earn that money, and they need that cash flow to keep running their business. Otherwise, they'd shut down, and then we'd shut down. We also need to avoid losing money. So we could lose hundreds of thousands of dollars a month if we were to just ignore the problem, which that's a lot of money. We need to ensure that our risk analysts are spending their precious time looking at the right shops and right credit card transactions. So here's some numbers about Shopify. $10 billion, that's US, cumulative processed. We've facilitated that much since we started 2006, I think? And 175,000 plus merchants, including some big names like Tesla Motors, Wikipedia, and GitHub. If you bought a GitHub t-shirt, that's through Shopify. 14K events a second, that's the number of events that are coming from Shopify. And that's about 1.2 billion a day, so it's a lot of data. I mean, not as much as the medical data, but it's still a ton of data to process. And then we have 5 risk analysts looking through it right now, looking through all of our transactions. I believe other companies have taken the let's just throw a lot of people at the problem and hired teams of hundreds of risk analysts. We kind of want to do it the smart way first and then hire up if we need to. So I said I liked hockey, and I'm going to deliver. Our risk analysts are kind of like goalies, right? That's my friend Alex. He's a very good goalie, but we're not a very good hockey team, so he stops a lot of pucks. And they're good at, he's very good at saving pucks, but if a bunch of people are shooting pucks at you, you're not going to be able to stop many. There's a lot of padding and not a lot of net space. So we need to build something that stops this hope factor of relying on the goalie. We need a system that can filter the high-volume event streams that Shopify application produces so that our risk analysts aren't overloaded. We also need to make sure we're not sending them the non-risky events as much as possible. And we need to make sure that we are sending them any actual risky events. So this is false positive, true positive, all that kind of stuff. We want to reduce their workload while ensuring there are no risky events that go unnoticed. Don't go unnoticed. So we built this thing that that's my friend Evan. He's a defender, so he's supposed to stop the pucks from getting to my friend Alex. And you can see he's patting my friend Alex on the back, so Alex must have made a good save, which means Evan shouldn't be smiling because he didn't do his job. So Spark streaming allows us to do real-time data processing. we can decide which events to take a closer look. We built a stream processor that filters down these event streams, these super high volume event streams, into not so high volume event streams. And then we do an HTTPS post for each risky event out to a custom built case management software. These risk analysts then open up that software, look through the queues, and decide whether events are risky. As an aside, we call it pat down. It's themed after what happens in an airport security line if you get flagged for closer review. So, necessary introduction to Kafka, Zookeeper, and Spark streaming. So who's heard of Kafka? Hands? So most of you, I'd assume. Zookeeper? Less so, but that's what Kafka uses for coordination. Spark streaming, or Spark in general? Yeah, okay, fair amount. So Kafka is a fault-tolerant and distributed publish subscribe message buffer originally written at LinkedIn. You define a list of topics and produce messages to these topics. So these topics are like order placed or product created or something like that. And then you consume those messages elsewhere later. Our main use for this is to be able to log events super quickly from the Shopify application so that we don't have to do a slow database call or like pulling the database from our external application. It's super fast to write these events. Like, it's very low cost. Then we need to be able to read these events from another application, say an automated mailer or a dashboard or dashboard for the sales team or something like that. So it has ridiculously high throughput due to some engineering decisions. Ridiculously is a technical word, I think. So it has a retention policy, which means that it'll only guarantees the events will be stored for X hours or days. Most of our topics are 7 days. It has an at least once guarantee, meaning you'll hear the messages at least once, but you could hear it twice or 3 times or 100 times or something like that. So you need some kind of deduplication if you care about that. These topics are also broken up into partitions, which you can see up here. So partitions are basically partitions of the data. And we want to ensure all of our data for a specific shop is on the same partition because ordering is only guaranteed within that partition. So if you care about these events in order from that shop, you need to make sure they're all in the same partition. And if it slows down, you add some more computers. So it's a money problem and not a computer problem. Just as a side note, like I said, there's a retention policy of 7 days. We actually have this thing that comes along, reads Kafka, and writes it down to HDFS. So we have an infinite retention policy if you think of it like that. So Zookeeper is used by Spark Streaming and by Kafka for coordination. It's a distributed data store that stores data in kind of a tree format, like you can see here. We store configuration details for Spark Streaming. Actually, here, I'll go back for a second. You can see these like indexes here, like 0, 1, 2, 3, 4, 5, 6, 7. Those are called offsets, and it's basically just like an event ID for that partition. When you're consuming from a Kafka topic, you store the event that you've received in Zookeeper, and it's a really well-written piece of software that's admittedly hard to use, but once you've got it working, it's working really well. If the streaming job ends up shutting down, we ask Zookeeper, hey, where'd we leave off? And it works really well for that. So here's Spark streaming. I'll kind of, since most of you put your hands up for Spark, I'll just skip over the intro to Spark stuff because it's easy to cover here too. It's a stream processing framework built on top of Spark. Spark is really good at distributed data processing. It has a little bit of overhead, but it makes it really easy for programmers to ignore the fact that your job is being run in a cluster. Its main level of abstraction is the RDD, which I believe stands for a resilient distributed data set. And it's just a data set that you can do map, filter, reduce, all of those standard operations on. So it splits up the data across the cluster for you so that you can get the fast parallel processing. And it's written in Scala, but it has a really good Python API. And at Shopify, the data team uses Python. That's our main language. I think probably most of you too, since you're here. Similar to Kafka, it has an at least once guarantee. Spark Streaming does, assuming you set it up properly. You can get it exactly once, but that's hard, and we didn't bother with that. We figured we'd solve the problem in another way. So it's all in memory unless you tell it to save it down to HDFS. That's useful for reasons we'll get to. Spark Streaming breaks up the incoming data into chunks and then puts it into an RDD that you can do operations on. This is called a discretized stream or dstream. That's the core abstraction. And what it is you basically microbatch the streaming data. So every 30 seconds, say, or every half second, you take all of your incoming data, put it into an RDD, process the RDD, and then keep on doing that infinitely, or until your job dies. The breaking up of the data, the timing can be customized. I think it's minimum 500 milliseconds. Maximum, I don't know if there's a maximum, but you should probably set a maximum because it stores it all in the memory. If you're serving web requests with Spark Streaming, you probably want to set it to the lowest possible because then you'll have the highest or lowest latency. These jobs need to be very heavily optimized though, because you won't be processing the data as fast as it comes in if they're not optimized, which is a big problem, and we'll get to that. We don't really care too much about this timeliness as long as it's within a couple hours. Like if the risk analysts have seen it within a couple hours, who cares? Like it's a 2-day, 3-day payout. So we set it to conservative 30 seconds, which allows for much higher throughput, but higher latency. Each batch Spark Streaming asks for a block of offsets from Kafka, creates an RDD from the returned event, and as I said earlier, if your processing time is larger than your batch size, you'll fall behind and you might not be able to keep up. So the way Spark still works, the way Spark Streaming works in most cases is using these things called receivers. Receivers, what they do basically is it loads chunks of data, stores it into a queue in memory, and then your Spark engine comes along after and processes the queued data. So again, if you're keeping up with your stream, you'd have one thing of queued data, and then you'd pick that up the second it's queued. So it's like super quick. It works pretty well. I'll give a demo of it up here. It's a slight simplification, but it should give you a general idea of how it works. So you have between T0 and T1. So these are your batches. T0 to T1 is one batch. T1 to T2 is another batch. So you have these events coming in from T0 to T1. The receiver builds an RDD out of those events. Then the Spark engine just picks it up and runs your defined functions on it. While that's happening, you also have more events coming in, build another RDD, process that, and then more events. So each time window, I already said that. Receivers are designed to work with all data sources, not just the buffered ones like Kafka. Like I said, Kafka, you can ask it for a specific event, and you can keep on processing from that event. There are other Spark Streaming data sources, like you can basically watch an HDFS directory, and any new files, you come in, you process it. But like, you can't, yeah?
So just to clarify, so the receiver is actually a function or an object in Spark, and then it's essentially acting as a queue
Yeah.
in front of the
Yeah.
Spark process.
Yeah, in front of the processor. It receives it, stores it into memory, and then when your processor is ready, it'll pick up one of those batches in order. That's the important part too.
It's part of the Spark Streaming API, right?
Yeah, it's part of the D stream. So there are a couple problems with receivers, at least for us. It's pretty great first start, but it wasn't really designed with Kafka in mind. It was designed with the general case in mind. So the first problem is checkpointing. The only way to get at least once delivery makes it hard to deploy new code. So what that means is it takes the data, like checkpointing takes the data that you've received. Well, checkpointing plus write-ahead logs takes the data that you've received, but have not yet processed, and it saves it to HDFS. So if your job fails, you just look at HDFS and say, oh, hey, look, there's some data there. We'll start off from there. The big problem with this is that it actually saves your set of instructions, your directed acyclic graph. Everyone's familiar with what that is? Yeah? So it loads that too, meaning you can never deploy new code. Like you can't. You just, unless you come up with like some tricky way of around it, you're just stuck using that code forever. Yeah, which that's not. Like in our case, we do update our code. So, could the code reload itself? I don't know. I don't. Yeah, I guess that could work, but you'd have to hack the Spark internals, I think. Yeah. So it's a little bit. I think it would be a hacky solution. But the other thing is, Zookeeper's updated with which offsets you've received when you receive the data, not when you're done processing with it. So if you don't have checkpointing on, here's what I was saying about the at least once guarantee. If you don't have checkpointing on, you will receive the data, tell Zookeeper, we're done, like I don't need to hear this event again, and then your job dies in the very first event. So you basically process none of the events. You basically process none of the events, which is problematic because then when you ask Zookeeper, hey, what have I heard? It tells you something that you've heard but not processed. And it also makes traditional Kafka monitoring tools less useful because if your processor's falling behind, Kafka monitoring traditionally asks, hey, Kafka, what's the latest offset? Hey, Zookeeper, what's the latest offset this consumer's received? And it kind of shows you a graph of how your lag, basically. So you want to keep it very low. And this, you can't really tell if your processor's falling behind, which is actually a problem. The last problem is it's kind of duplicating work because Kafka already has this buffer, so why have two buffers? Again, receivers were designed for the general case, which is not, Kafka is a very specific has some very specific engineering choices, which makes it better to do it with something different, which receiverless. This was added, I think, maybe January or later, and it was presented at the Spark Summit, and it's pretty awesome. It's specifically designed for Kafka, although I think other data sources similar to Kafka might start using it. You handle all the offset management yourself, which is unfortunate. You have to actually pull the offset, figure out what offsets are, know how to talk to Zookeeper and do all that stuff. But you get a lot of power with it. So the best part about this, in my opinion, is you can tell Zookeeper after you've actually processed the data, after you're done with that batch. So if there's a problem before that, well, you just replay data. And that's where the at least once guarantee comes in. You might process half of your batch, and then it dies, and then the rest of your batch is unprocessed. But then you just start up from there again. You reprocess all those events, and then process the unfinished events, and then update Zookeeper. Again, the downside is there's a lot more work when it comes to Zookeeper management. You actually have to write code to figure out how to talk to Zookeeper, how to talk to Kafka, and do all this stuff yourself. The receiverless approach actually does all this for you, which is kind of nice, but again, there's problems with that. So hopefully it'll mature as Spark Streaming gets older, which I think that's the plan, and they might provide us a nice simple API to say rdd.commit or something like that. Say I'm done with this one. A downside of this, another downside of the receiverless approach is the API for Python is not quite at parity with the API for Scala. It's getting there slowly, but the way they work is they implement the Scala code, and then someone else comes along and says, hey, I really could use the Python API, so they add it then. The documentation is also not up to date, so it'll say you can't do a lot of the things that you actually can do in Python. So it kind of discourages you. You're like, damn it, I can't do that. But then you look at the code and it's like, no, it's there. You can do it. So I've been updating some of the documentation there as I have encountered it. And then the main downside is it's super experimental, and we're okay with that. So how it works, here's another diagram, is you get some events. Then the next time you process those events, and then you update Zookeeper. And then you get some more events that time, and then you process it. So it's a little bit simpler, as you can see. There's no receiver in the middle. So the general structure of how we built our streaming jobs, we don't use checkpointing again, and it's not necessary to get that at least once guarantee. You load the Kafka offsets from Zookeeper if they exist. So you ask, hey, what have I processed up to? If not, you start from earliest or latest available offset, whatever is your choice. Then you tell Spark Streaming to create a D stream that consumes from Kafka, starting at the specified offsets. You define your processing step like filter out your non-risky events. You define your output step, like post the data to a case management software. And then you actually save those offsets of the most recently processed event to Kafka or to Zookeeper, and then you actually start your streaming application. Like I was saying, you define your DAG, and then you start it after you've defined it. You can't add new steps after you've already started your streaming context. So here's the example that I'll give you guys. We filter risky products. So hair extensions are apparently an industry standard for super risky products. You guys know what that is? You attach it to your hair to make it longer. Apparently that's just almost always fraud. And then a couple of the other things. I don't know what a Wi-Fi pineapple is, but I think it's like a jam box or something like that, similar to that. Travel package, that's just because you're not allowed to sell air travel over Stripe, which is what powers our payments provider. And then vaporizer, all the other things, iPhones, pharmacy, and then cannabis, which is legal to sell, but we still want to look into it in case they're trying to sell it over Shopify payments, which is not allowed. Gucci too. I don't understand that one. So here's roughly how it works. And this is just for one batch. Like we're just gonna look at this as just like one batch of 30 seconds for us. So we get all of these products. Well, these are product titles, for example. So hair extensions, nice shoes, sweet bag, cannabis, Taylor Swift t-shirt, I'd buy that. And then Gucci. And then you run the filtering step on it to filter out things that aren't risky, or rather things that are, filter in things that are risky. You do some mapping on it that just like converts it to a JSON object, which you can then post to our case management software. And this is a bit of a simplification. There is a lot of code involved behind this, but here's the bulk of our streaming job. Like we just do a map, filter, some filters, we format the record, we format these things called triggers, and then we do a check of our output contract, which just makes sure that all the types are what we expect them to be and all the fields are there. So here's one thing that is quite important in streaming jobs. So some streaming jobs, say the risky products one, all you need to know about that event is contained inside of that event. Like that event has everything you need to know to decide whether it's risky or not. But sometimes you might want to ask like, okay, tell me the shops that have had orders in the last hour of over $10,000, and we might want to look into those, especially if they're like newer shops, because maybe they're just like testing a bunch of stolen credit cards, right? So the built-in time windowed functions aren't quite ready for prime time yet. They window based on the received time of the event, not the time the event was created. So you send out your event from Shopify, and then you receive it 3 days later by the streaming application. That will be included in like the window kind of weirdly. It also requires checkpointing to be enabled, which, as discussed earlier, has its own limitations. You need checkpointing because you're not going to be able to hold all of this data in memory. You need to save it somewhere. So they use checkpointing like that. There actually is kind of a workaround for this, but I won't get into that. We haven't done it yet, but we're planning on implementing our own time-windowed functions that get around some of these shortcomings. But TD, or TDAS, I think is his GitHub handle, he's the core developer of Spark Streaming. He's actually said that, hey, if we build some functions and everyone just builds their own anyways, like those functions aren't good enough. So they're going to be working on this, I think, in 1.6 or 1.7, which is very welcome. So the future. Time-windowed functions. That's kind of a necessity for the non-trivial jobs. Again, in the case of if you want to know aggregates for the last hour or 3 hours or something like that. Performance tweaks. So our jobs have just, like we wrote them and they've just managed to keep up. They haven't been super taxing. We haven't spent any time on this. So there's a potential for a lot of gains, but we haven't really needed to. We haven't done anything super complex other than, say, checking that event against an in-memory list of things called a broadcast in Spark. And then we've done a couple joins. You can actually join dstreams to RDDs, which might like be a historical data set that you're interested in. You can join dstreams to dstreams too. You can do a lot of cool stuff. So machine learning, here's the one that probably most of you will be interested in. I think this is like a fairly data science-y conference. So we have these risk analyst decisions in this case management software. We can actually build a model about these decisions, like using that as like the ground truth, or like the 1 or 0, the true or false. And then we could probably build some smart models, not even necessarily relating just specifically to like product events, but maybe shop events or something, shop-related events. So improved monitoring. We're only monitoring the basics right now, like processing lag, and then number of events processed per minute. But you might want to monitor something like how much time it takes to process each event on average, different things like that. The next thing, another buzzword, Apache Cassandra. It's actually pretty cool. You can use it as a very fast key value store for your job. So say if you want to, every hour you want to build a data set for the last 10 days, which is outside of our retention policy, and you want to check each event against that built data set, you can store that into Cassandra, and then when you want to look up the value for that shop, you can do it without actually having to use the time-windowed functions, because again, the retention policy is only 7 days, so you can't do 10 days of aggregates. And then an improved receiverless API. Like I was saying, you have to do all of this offset management yourself. So I kind of want to work on something like that where you can just do rdd.commit when you're done with it, like when you're done processing, and it will just handle all of that stuff for you. So a slide for icon credits. I used some icons from this awesome project called the Noun Project. They have free icons. Some of them you don't need to give credit for, some of them you do. We're hiring, shopify.com/careers. So if this interests you, come talk to me or go to that website. And then thank you. If you have any questions, you can tweet at me or I guess find me on the website, at the conference website. This was a longer talk last time because it was a more chatty of a group, but I assume you're all holding your questions until now. So questions? Yeah?
Kafka, right? I'm just asking. The buffer itself is distributed or just one?
Yeah, it's distributed. So if the question was, is Kafka distributed? Like, is the buffer distributed? Yeah, if the level of parallelism comes from those partitions. So if you have like a replication factor of 1, which means like if you lose one node, you'll lose your data for that node. If you have a replication factor of 1 and you have 10 partitions, you'd have 10 nodes. You might set the replication factor to 2. I think ours is 3, so we could lose up to two nodes and not have data loss. And that's scoped to the partition. And each partition has a leader, like who's the most up-to-date person, and then it handles all of the synchronization behind the scenes. So yeah, if something slows down, you add more computers.
I can also, like, for example, I have two multiple streams, right? Let's say if guys coming from one exchange, another coming from, I can build a graph, RDD graph, a separate graph, integrate both, right?
Yeah. So the question was, if you have two streams, you could join them together into one stream and do operations on that. And the answer is, yeah, you can union streams, you can do joins on streams, you can do like, yeah, it's on the Spark streaming API, yeah.
From a machine learning perspective, the at least once guarantee of Kafka is pretty awesome for monitoring your events. But when you start building real-time prediction models and you need to train them, having multiple repetitions of a risky event might overweight the occurrence of that event in your machine learning detection algorithm.
Yeah.
Do you guys have an understanding of when Kafka fails, how many repetitions of the same event you have observed over time? Because when you start building up these risk models, that's going to be a pretty important component for your outlier.
So the question was, have we looked into ways of getting around getting an exactly once guarantee?
Yeah.
Because it's dangerous when you're building models, you might duplicate events, like machine learning models. So we haven't really had that much in the way of duplicated events. It's only when our streaming jobs die that we ever get these duplicated events. There are a couple ways. I actually meant to talk about that, but I guess I forgot to add the slide about just the ways that you can get exactly once. There's two main ways. There might be more, but it's the ones that everyone talk about. Idempotence, which means that if you send the same event to your thing twice, it'll just know that it's already heard that and it won't do anything with it. And that's what we use. Our Rails app, like our case management software is a Rails app. It is just a database constraint. We craft an identifier based on a couple things and then send that off the Rails app. If it hears it again, it's just like, cool, already heard that, great. The other way is to use, I'm less familiar with this way, but you can, if you have a data source that you're streaming to, and that data source is transactional, you can actually update Zookeeper after every single event using the offset. Yeah, it's not the easiest. So every event, or the other way would be to transact the entire batch. So if you have like a half-second batch, you start the transaction, insert, or multi-insert, or whatever the command is, and then commit. And if it fails any time before then, your database will roll back. So that's like the better way of doing it for a couple reasons, but idempotence is just easier, and I like the easy way. So, but there are a couple other things. There's a couple theories on that. I think most people with the machine learning models, they generally try and build them, once a day, or like once every week or something like that, and then just use the built predictor. If their data doesn't change too much. If your data is changing really fastly, then that's a bit of a problem. You want to be able to update it in real time. It's a hard problem. Yeah, I think the joke that the other guy who gave a similar talk to me said, if someone tells you they're going to give you exactly once, they're trying to sell you something.
Thank you.
Any other questions? Yeah.
What are some of the advantages and both pros and cons compared to other technologies that use stream processing, such as Celery, which I've also heard?
So The question was, what are the advantages to Spark streaming compared to some other technologies? And I actually forgot to add a slide on that too. I did give this talk a couple weeks ago, and I had these written down, and I guess I just forgot to do it. So we tried a bunch of them, not Celery. We tried Storm. We tried, I think Sam's is another one. I was not the one doing that. I was just handed Spark Streaming, and then I built it. But I do know the reason why we chose Spark Streaming, and it just comes down to developer simplicity. We already use Spark. So the onboarding time for training, like a new data scientist to build a streaming job, is like, hey, here's the slight differences between our existing stack to the Spark Streaming stack. Here's some things you need to think about when you're developing a streaming job versus a batch job. Go. And Anshu over there, he built one. He onboarded pretty quickly and had a PR out within like a day or two, right? It was pretty quick. So there are criticisms of Spark Streaming. It's fairly immature, and they're kind of in shipping mode. They're trying to get as much features out as possible, so it kind of leads to some bugs that come out. But it actually has been working pretty well for us, and has been some of our most reliable Spark jobs running, actually. The engineers have told me. I think the industry standard is Storm, and we are pretty seriously considering Storm. I think Parsley gave two talks on Storm yesterday, or at least one was about Storm, the other one was, it touched on Storm. And yeah, we were seriously considering that, but the thing that we went with Spark Streaming was because we already ran Spark.
What's the rate of your message in your application like this?
Sorry?
The rate of message.
A lot. The ones that we're actually processing right now, the ones we have stream processing jobs, we have about, I think, 6 or 7 in production. None of them are too high volume. I think the highest volume is like 1,000 events a second, which is like really like nothing at all. We have, like I said, about 14,000 events a second in total. I think that's probably, since I gave this talk last time, I haven't updated the number. I think it's probably about like 18, 17. That number goes up super quickly. It's kind of scary. But yeah, you add more computers if it slows down. Sorry?
You get a real-time response.
It's pretty quick. Well, ours is 30-second batching, so an event's produced, and then Spark Streaming hears about it. It might take up to 30 seconds, 30 seconds plus some amount to receive it. But you can set it for like 500 milliseconds.
30,000 messages, basically.
Sure, yeah.
How many nodes are you processing against?
Are,
The events?
for which, sorry?
For the amount of events that you're processing.
Sure. Okay, so the answer to this question is kind of complicated. We use, and the question was how many nodes are we using to process these events? So we use Yarn for resource allocation. Everyone's heard of Yarn, or like at least been introduced to it? So yeah, we have these configuration options that say give this job this many cores, this X, this Y, and we kind of just went with like pretty liberal defaults, and we probably use a lot more resources than we actually need. Our cluster itself is about 60 nodes. That's for Spark and for Spark Streaming, but like the actual resource that these jobs use is minuscule. Like you could easily run all of our production jobs on your laptop. Yeah, like, and in fact that'd be faster because there's no like parallelism going on. So, yeah. Sorry?
As a follow-up, I'd be interested in, after your comment, why you decided to co-locate your normal Spark job with your Spark Streaming job.
Like in the same cluster?
Same cluster. Right?
The question was, why do we put our Spark Streaming jobs with our Spark jobs? It was just easy. We already had the infrastructure. It was set up, and it's been working so far. I think we're actually going to be separating that out in the future, but for now, it's been working. So.
I'm actually curious about the interface as well as kind of the structure of events that they go in Kafka. So is it loosely defined JSON objects that you're putting in there, or is there some sort of conventions that Shopify follows?
Yeah, this one's a bit of the question was what formats the data in Kafka. This one's a little bit of an embarrassment. It's JSON. So like our data engineering lead jokes that we're burning down forests in the Amazon when we really should probably switch over to a better, or not better, JSON's awesome, but like a more efficient format. We do have raw like Nginx logs in Kafka too, but any kind of event that we're processing with this risk stuff is probably going to be a structured JSON event.
So are those structures basically like custom structures that Shopify follows, or is it ad hoc depending on the nature of the event?
Oh, yeah. Yeah, so the question was, are these structures like schema'd, I guess? So we kind of messed up when we first started with Kafka. We had another logging system that we had built before that kind of had like topics, which is the Kafka concept, and then event names, which the schema was on the event name, not on the topic. We have like a checkout flow for where you go to put your credit card, an admin flow where you actually go to administer your store, and that's what our events were scoped to, was this topic. How much time do I have? 2 more? Okay. So yeah, the schema was on the event name, and we're trying to migrate actually towards a topic level schema, which we're in the process of. All new events are basically going to be topic level schema, but right now they're schema'd to this event name field. And back on your other question, or the question that I thought you asked, we're actually trying to move to Avro and some other, like some pairing of the two. I'm not too familiar with like those, but that I think offers a schema and also offers a more efficient message format. It's just like, this was just like, we try to go the easiest approach first and then change it after. It's just the quickest way to ship features, right? So.
Is there a way to keep the consistency of the order of events across different partitions? Because let's say if you want to replay the exact same event, and it had to happen.
The consistency of order on a partition?
Across.
Across partitions, not easily. The question was, can you keep order across partitions? The answer is not easily, and the reason is complicated. If you have any more questions, you can come talk to me too, or tweet at me, the things up there. I just changed my Twitter handle because my old one was like impossible, so I hope that's correct. But yeah, it's correct. I tried it. Yeah, so thank you.